This morning, it is my pleasure to introduce Dr. John Callas from NASA's, he's the project manager of the MER opportunity, which we're praying to hear from. And he is the manager of NASA's NSF Exoplanet Observational Research at JPL. And welcome, Dr. Callas.
Thank you. Good morning. As mentioned, one of my other hats is project manager for Opportunity, and you know there's a dust storm raging on Mars. It's been over 70 days since we heard from the rover, so we're all hopeful, but stay tuned. So Mars is a tough place. But I want to talk to you about not endoplanets, but exoplanets. As you know, it's an exciting, exploding field of discovery, and so hopefully I'll give you a little sense of that this morning. So first, just a little bit of background on some of the ways in which we detect planets around other stars. One of the common techniques that you'll hear a lot about is the transited method that you see here as an animation, where as you look at a particular star, a planet in question passes in front of the disk of the star, and you get a dip in the brightness of the star. The depth of that dip is proportional to the ratio of the area of the planet versus the disk area of the star. So you can get in the radius of the planet that way. But it has some limitations. One is that the orbit plane has to be nearly edge on to see it. And so you really only see about 0.5% of all transit candidates that might be out there. But still, we've detected thousands of those, and you'll hear a little bit more about that from the next speaker. Another very powerful technique, which was actually the first technique to detect exoplanets, is what's called the radial velocity technique. And that as a planet orbits around a star, it makes the star wobble. Much like if you have a rock on the end of a string and you spin it around your head, your body reacts to the motion of the rock, and so the star reacts to the motion of the planet. Now, you don't see the wobble directly. What you see is a Doppler shift to the spectra of the star as it orbits, but it's a very small effect. Now, I'll give you an idea. A Earth-like planet around a Sun-like star will induce only a 9 centimeter per second Doppler shift at its peak. And that's over an entire year, so it's a very slow effect. You're not looking for a star that's wobbling in real time, so you have to sample it over time. And because it's such a tiny effect and much, much smaller than many of the other noise effects, you have to do a tremendous amount of spectroscopy. So you actually examine about 4,000 spectral lines simultaneous, and you look for a slow sinusoidal variation to the position of those spectral lines. And it's a technique that we've been very successful with, and so we've detected a number of planets. Of course, the holy grail is direct imaging of planets, and we're just starting to be able to do that now. This is an image taken with the Gemini telescope using the GPI, or the Gemini Planet Imager. It's an occulter, so in the center you see there is a disk that's been blocked out that blocks out the light of the star, and you can see just to the lower right, you can see a large luminous object, and that is a massive Jupiter-like planet. The scale of this image is that that's roughly a Jupiter distance if this star was about 10 parsecs away. We obviously would like to look closer into the planet and look for much dimmer planets. The contrast ratio between our sun and our Earth in visible wavelengths is about 10 to the 10th. So occulters or coronographers have to suppress that starlight by a factor of 10 billion. And that's really, really challenging because light diffracts around any kind of object. But we're trying to push the state of the art to be able to attempt direct imaging. And I'll say a little bit more about future missions on that. So here's a survey, and this was just updated last week, of the confirmed exoplanet candidates that are out there. And there are about just under 4,000 objects on this chart. And you notice the red and the green, and those are the transiting method and the radial velocity method, which are right now the dominant techniques for detecting exoplanets. And you'll notice that they're clustered in groups. Notice that the transiting technique is shifted a little bit to the left in orbital period. Notice those are very short period orbits. The scale at the bottom is logarithmic, so around 10 days. And that's because it's a lot easier to detect a transit if it happens frequently, because you can look at it and you can see it often. If it takes years for the transit to occur, like it would happen for the Earth and the Sun, obviously you have to spend at least several years getting at least a couple of transits to occur. So it's easier to get the short period ones, and so we have an observational bias that way. And if you look at the radial velocity technique, notice that cluster is shifted up. On the left-hand scale is in Jupiter masses, and so notice that the planets that have been mainly detected are Jupiter mass and greater. That's again because this wobbling technique, the more massive the planet is, the larger the effect. In the case of our solar system, Jupiter induces about a 12 meter per second Doppler shift in our sun versus the Earth, which only does a 9 centimeter per second. So there's 2 orders of magnitude difference there between the two. So both of these techniques have an observational bias. And you can see there are a few other techniques that have been used: microlensing, direct imaging, timing variation, and astrometry, among others. Also mentioned, the big difference between radial velocity and transiting technique is the transiting technique can give you the radius or diameter of the planet. The radial velocity technique can get you the mass of the planet, at least to within a sign of the inclination of the orbit. And those are powerful measurements. So here's a plot as a function of time of the number of planets that we've detected. Now, when I went to school, there were 9 planets. And then there were 8 planets. And now we have thousands of planets. But you can see here that the radial velocity technique in red has consistently improved, and the longer we look, the more we find. The green, the explosion in the green you see here is mainly due to the Kepler mission. And I'll say a little bit about Kepler in just a little bit. So if you take these observations, so we have detections, we have thousands of detections, thousands of confirmations, but we are now entering the mode of characterizing these exoplanets. So this chart takes a set of Kepler observations where we have both the radius from the Kepler observation and the mass from radial velocity techniques. So we plot them on a graph of mass versus radius. And you can see a variety of curves. What this allows us to do is now characterize these exoplanets, because if you have the mass and the radius, you have the density. And you can now infer something about the composition of the planet. So if you see those curves that increase to the right, notice at the bottom there's one that's 100% iron. That would be the density of an iron planet. And as you go up, you can see that there are ones that are 50% iron, 25% iron. Then you can start to see the silicates, the oxides, so the traditional minerals. Then you can see the water worlds, 25% water, 50% water, 100%. And then to the upper left, you see the gas giants. And so now we can characterize these planets as whether they're rocky worlds, potentially with water, or whether they're gas giants. And so we now have a powerful tool for the characterization, not just only the detection of exoplanets, but the characterization. And you can see there are hundreds of candidates just on this chart alone, which is a small subset. So this is our arc of missions right now, or our roadmap, if you will, of NASA's objectives for exoplanet exploration. So the upper arc, you can see the Great Observatory. So you have Hubble, which has been a phenomenal instrument. You can see Spitzer looking in the infrared. Kepler, which has been this tremendous workhorse in detecting exoplanets via the transiting technique. The next mission that's flying now is Tess, that you're going to hear about from my colleague from NASA shortly. And then we hope to launch the James Webb Space Telescope in a couple of years. And then further out is a mission called WFIRST, the Wide Field Infrared Survey Telescope. And I'll talk more in detail about that. The Europeans also have a set of missions. Corot, Gaia will launch soon, and then Cheops and Plato. And then there are a set of future missions way out there. These are NASA probe studies. that will be large aperture space telescopes that may include technologies like Starshades. Down at the bottom, there is a ground-based component to this. We're using the Keck observatories for radial velocity and follow-up confirmation. We've been using the Large Binocular Telescope Interferometer to examine dust rings around stars. And then my mission, my project, and an Explorer, which I'll talk about in detail, is a state-of-the-art radial velocity spectrograph that will greatly complement missions like Tess in helping us to explore further, deeper into space for exoplanets. So Kepler has been this phenomenal success, detecting thousands of exoplanets. But we have to remember, Kepler was looking at a small region of space, a small part of the sky, roughly 150,000 stars. And then in that 150,000 stars, it found thousands of exoplanets. But remember what I said earlier, the transiting technique typically only sees 0.5% of the stars, only those candidates where the orbit plane is edge on to the observer. So if we're only seeing 1 out of every 200, instead of those roughly 3,000 to 4,000 stars, there should be something of the order of 600,000 stars, I should say, planets, 600,000 candidate exoplanets out of 150,000 stars. So do a little math here, 600,000 divided by 150,000. You're finding that pretty much every star not only has an exoplanet, but a planetary system. And pretty much every star that we have the technology to examine is showing the presence of planetary systems. And in these planetary systems, small rocky planets are common. And planets, small rocky planets orbiting in the habitable zone are common. One of the notable celebrities in this category is the TRAPPIST-1 system. So here you see a diagram on the upper part of the TRAPPIST-1 system. It's an M-dwarf star, so it's the star is very small and dim. These planets orbit very close to that star. They are rocky and Earth size, but they orbit in that star's habitable zone, which is much closer in because, you know, the star being dimmer, the habitable zone is much closer. You can see the TRAPPIST system compared to our solar system, so you see that the entire system would fit well inside the orbit of Mercury, much, much smaller than the orbit of Mercury. And further, these planets are tidally locked. They orbit so close to the star, they always show the same face to that star. But these systems are not unique or unusual, but are proving to be common. M-dwarfs are the most common category of star that's out there. But again, we're finding that when we look with the right instrumentation, exoplanets, rocky exoplanets orbiting in the habitable zone are quite common out there. And this is profound, this is exciting. So we're all very excited that the Tess mission has launched. Tess, unlike Kepler, is going to look at the entire sky. So our expectations and our hope is that Tess is going to be this magnificent fire hose of additional transit candidates out there, and will further expand the envelope of exoplanet study to a great extent. So in support of Tess, which is going to give us these candidates and give us the size of these candidates, the radius of these candidates, NASA is funding a mission to build the state-of-the-art ground-based radial velocity spectrograph. And it's going to the WIN telescope at Kitt Peak. The WIN 3.5 meter telescope will have 40% of its observing time dedicated to using this state-of-the-art spectrograph. Right now, the state-of-the-art is about 80 centimeters per second. That is the smallest radial velocity signature that we can reliably detect. That's the HARPS spectrograph for those that are familiar. But Earth-like planets have radial velocity signatures that are many, many factors smaller than that. So we want to push the envelope on what we can detect with the radial velocity technique. So it is my job and my objective to produce this spectrograph that will get below 30 centimeters per second. So we'll be roughly within a factor of 3 of Earth-like planets around G-type stars. And we will use NN Explorer to follow up the candidate observations from Tess to add the mass observation to those, and then we can do the density and the characterization. And Tess is going to generate many, many more targets than we'll have time to look at. So not only NN Explorer will be out there, a future spectrograph, the Europeans have one called Espresso, which will have comparable performance. And we're working on the Keck Planet Finder, which is another spectrograph that will go to the Keck Observatory, that will go to one of the 10-meter Keck observatories. So we are rolling out these additional tools, these powerful instruments that will allow us to do this characterization. But transit technique and radial velocity technique are just two of the several techniques that we can use to study and characterize exoplanets. Sort of the holy grail is direct imaging. Now you're told you never look at the sun with the unaided eye. Well, we never look at a star without the proper equipment. And what we would like to do is to be able to directly image exoplanets around stars. But to do that, we need to suppress the starlight. So we need to occult the star. And we are working on coronagraphs that will do that. Right now, the state of the art in coronography is suppression maybe in the 10 to the minus 4, 10 to the minus 5 range. We need to get to 10 to the minus 10 and beyond. So one of the technologies or exploration areas is in internal occulters, to build these instruments that within the instrument we can block that starlight, reduce the diffraction, and to be able to see a dim companion to a bright star. But that's really not enough. What we'd like to do is to be able to look in close to the star, because coronagraphs have a limit to their inner working angle, how closer to the star they can suppress and block that light. So one additional approach is to use an external occulter, or what we call a star shade. And this would be to make a space-based shade that flies independent of a space-based telescope and can fly far away from that telescope, maybe of the order of 50 to 100,000 kilometers away from the telescope, and suppress the starlight. That allows you to get to much, much smaller inner working angles. Additionally, you're suppressing the light before it ever enters your telescope. And so it greatly simplifies the complexity of diffraction and reflection and non-uniformities and irregularities in your telescope. So NASA is funding an ambitious technology development program, and you can see this collage of technologies here. In the upper left is this technology of developing these coronagraph masks, these small little devices that will block the starlight within an instrument, within a telescope. In the upper right, we're looking at large deployable and monolithic mirrors to fly in space, to make even larger space telescopes. One of the challenges, though, is you want to be able to get this thing into space. The largest single-size mirror you could fly right now on the SLS is probably about a 4-meter diameter mirror. We'd like to have tens of meters of diameter for these apertures, so that means segmented mirrors. So we're looking at technologies that can deal with the imperfections you get from a segmented mirror. Those of you that are familiar with this know that all the edges produce artifacts off your mirror that you have to deal with. So there are techniques for modulating the light as it comes in, to controlling the phase of the light that enters your telescope, removing the non-uniformities or the non-planarity of those signals. So you see in the lower left and lower right, technologies that are being advanced to do that. As far as Starshades are, we are also working on developing independent deployable star shades. They have to fold up. There's a magnificent origami of these structures that may be 30 to 100 meters in diameter that have to fold up so they can fit in a rocket fairing. And so you can see here along the bottom of this image some of the technology that's being developed right now at JPL. The challenge is this 50 to 100 meter scale structure actually has to be stable to within a millimeter. In fact, part of the structural edges on this thing have to be controlled to within hundreds of microns in stability once it's deployed, because little imperfections can actually allow significant amount of diffracted light to eventually enter your telescope. So it is a engineering challenge to build these things, but we actually think we're on a path to do this, and we're working towards getting a flight Starshade. I mentioned early on a mission called WFIRST, the Wide Field Infrared Survey Telescope. This is the next space telescope after the James Webb Telescope. So it'll launch in the late 2020s. It is a 2.4 meter single aperture telescope. It's taking advantage of a surplus National Reconnaissance Office spy telescope. It will have a phenomenal infrared performance and a tremendous field of view. It'll have a capability that's 100 times that of the Hubble Space Telescope, but it'll also fly a coronagraph. And that coronagraph right now, we hope to be able to achieve maybe 10 to the minus 6, 10 to the minus 7 contrast ratio. So maybe we'd be able to directly image perhaps Jupiter-like exoplanet candidates around sun-like stars. Doesn't quite get us to 10 to the minus 10. That'll be a future mission. But we also intend to have it Starshade ready, meaning that a subsequent launch, we could launch a Starshade that could rendezvous with WFIRST and provide that external occultation of the star to be able then to try to image Earth-like planets. And you can see down at the lower bottom, you can see the performance of a telescope without a coronagraph. The middle frame shows the kind of performance you might get with a coronagraph, and then with a mask and deformable mirrors, you might be able to actually resolve a planet around a star system. So this is very exciting. This would really pathfind the technology that we would need to directly image exoplanets. But of course, that's not the end of the story. NASA is working on a set of probe studies, and these will be part of the next decadal survey in the 2020 decadal survey. And they're looking at 4 missions. 3 of them have exoplanet capabilities. One is called LUVOIR, the Large Ultraviolet Optical Infrared Telescope. It will be a sort of James Webb-like telescope that'll have segmented mirrors, but it may be anywhere from 12 to 15 meters in diameter. It has a large thermal shield. Then there's the Habitable Exoplanet Imaging Mission, or HABEX. That may be a monolithic, a single mirror, off the axis, so it's an unobstructed pupil, more focus on exoplanets. And then there's the Origin Space Telescope, which is more of an infrared instrument. And all of these could fly with a Starshade to allow us to directly image planets sometime into the next decade. So I know this is the Mars Society, but maybe in time you'll have to change your name to the International Planetary Society and set up a travel bureau, because we will be able to characterize and observe directly potential worlds out there, and we'll wonder what it's like to go visit. And maybe that will be your job in the future. So I'll stop there. Thank you very much for your time, and I'm glad to take any questions. Thank you. Thank you. Thank you. Okay, several questions. I'll start with the microphone.
I understand it's difficult to line up the Starshade with a given star, but how difficult is it then when you get done with that, you want to observe another star at another location, if it's 50,000 miles between the telescope and the shade?
Right. You bring up an excellent challenge with using a Starshade, is that with a regular telescope, you can just point to whatever target you want. But if you want to look at a candidate that is on the other part of the sky, then you have to fly the Starshade, and it may take weeks to get there. And so they look at strategies where they plan out observations where your candidates sort of follow a path through the heavens, and they fly the Starshade to those. And then while you're waiting for the Starshade to go to the next target, you still use your telescope to do all the observation. You know, the reality is that every space telescope is going to be so heavily oversubscribed for observations, there'll never be a shortage of looking at a target. But yeah, you do bring up an important limitation of Starshades. Yes, sir.
Yeah. What about interferometers, either free-flying or on, say, the moon? which would give you the ability to have much higher resolution with telescopes of modest diameters each?
Yeah, excellent question. You bring up the question of interferometry. Yes, that's actually on the technology list. You know, we looked at interferometry. NASA had a mission called SIM, and found that it was really, really challenging. But it still holds a lot of promise, and it would be powerful for astrometry, which is another component of exploration that we'd like to engage in. And there are people working on interferometers. But currently, there's no NASA mission that's talking about interferometry just yet.
So I know it's a young science, but so far, what we're finding is that our solar system looks to be atypical in that we've got a lot of small terrestrials, not a lot of super Earths, not a lot of mini Neptunes. Are there particular instruments or techniques that could be optimized for discovering this grand tack idea, migrating super Jupiters or migrating gas giants that could affect what happens in the inner solar system?
Yeah, again, another excellent question about our solar system appearing to be atypical. What I will answer it this way, in that the techniques that I talked about, principally radial velocity and transiting, have observational biases. And so they tend to look for planetary systems that are very different from ours, because rocky planets are hard to detect that are close to the star. It's easier to detect gas giants. So we were understanding those biases. So as we go through and observe, we have to remember that we're only seeing a biased subset of the planetary systems that are out there. So I think in time, as we expand the envelope, we'll know better whether we really are atypical or not, and explore these questions about planetary migration during the history of a planetary system. Yes.
For the transit system, you mentioned the 0.5% number of planets that you detect of all the planets are likely out there. What are the assumptions underlying that 0.5% number, and what's our level of confidence in that number?
Oh, okay, so the 0.5% number, yeah, I should qualify that, and that is for a Earth-sized planet, 1 astronomical unit from a sun-like star. And so you can do a Monte Carlo of that, of any random orientation of the orbital plane, and you find it comes out to about 0.5%. So the number is smaller if it's a larger planet or larger star, or if it's closer in. So yes, I was a little casual with my 0.5%, but it gives you the idea of the scale of that number, and so we have to correct all of the observations with numbers that range over that kind of space. Yes.
Yeah, are you finding most of the transit in the galactic plane?
Yeah, so most of the stars, most of the exoplanets are in our galaxy, and they are in the galactic plane. I'm sure our next speaker will... Oh, is there a particular orientation to the orbital planes of these planets? I can't speak authoritatively on that, but my sense is that we do see them randomly distributed in space, so there isn't any particular alignment for them.
Okay.
Yeah.
Can you tell how stable the orbits are of these planets, and how does that relate to the age of the star?
I guess I can't really speak to the stability. Part of that is, we need observations of these systems over longer time frames to see if we can see variations in their orbital parameters. I mean, the techniques do give us some of the, we get the orbit period, we get the eccentricity, inclination, but these are snapshots in time. Just like, it took centuries for us to see the precession of the perihelion of Mercury in our own solar system. So I think in time, as we collect more statistics on these things, we will begin to probe questions about stability. But that's an excellent open question right now. One question, yeah, okay.
In light of your findings, can you speak to the Fermi paradox?
Oh,
Great question.
well, maybe I'll address that this way. In this modern world where pretty much everyone has a smartphone, I still find it a really hard time getting a hold of people. And so if it's this hard for us here on this planet, can you imagine how difficult it is going to be on interplanetary scales? Okay, thank you very much. Appreciate your time. Thank you.